To continue with the feature engineering steps, we're going to capture the elapsed time between the year in which the house was sold or remodeled and the year in which the house was built. We use the same functions that we saw in the exploratory data analysis. So briefly, the elapsed years function takes the data frame and the variable that I want to transform, and then it determines the difference between this variable and the year in which the house was sold. So now I apply over each one of these variables the elapsed time calculation that I have here, and then once I do this, I remove the year sold variable from the dataset because I don't need it anymore. Next, we're going to apply some transformations to the variables. We're going to start with the logarithmic transformation. So for each one in these three numerical variables that have only positive values, we apply the logarithm, and then we apply on the lot area the Yeo-Johnson transformation, for which we use the stats Yeo-Johnson function from the SciPy stats module, and we pass the variable that we want to transform. This variable returns two values, the transformed variable and the parameter that it used for the transformation. This parameter is learned from the training set, as we do here, but to transform the test set, we need to use the same parameter. So in the function, we are going to pass the variable in the test set, but we're also going to indicate that the parameter is the one that we determined before, which we can also print here. We decided that we're going to use these transformations based on the exploratory data analysis in the previous section, and also a little bit arbitrarily to try and show you different things throughout the course. We're going to linearize the variables that are extremely skewed. These are the very skewed variables that we found in the exploratory data analysis. So for each one of these variables, with numpy npwhere, if the value is 0, we keep a 0, but if the value is anything else, we will just replace it by 1. Now we're going to transform the categorical variables. We had variables that had specific mappings given by an arbitrary graduation determined by a person. So for example, we have these variables that take the values POO for poor, FA for fair, average, good, and excellent. So we're going to replace these labels but increasing numbers. And this is what we do with the map function from pandas. We did this also in the exploratory data analysis, so I'm going to go quicker. We have other specific mappings for the basement exposure variable, specific mappings for the finished variables, for the garage, and for the fence. For the remaining variables, so those that we did not encode with these specific mappings, which we capture in the cat others variable list, first we're going to find the frequent labels, and here is a twist over the function in the previous notebook, because we're going to retain the variables that are bigger than the percentage of rare labels. So here we are not retaining the rare labels as we did in the previous notebook, we are retaining the common labels. In order to do this, we group the data frame by each of the variable, and then we count the number of observations, and we divide by the size of the data frame to obtain the percentage. Remember that we can also do this with value counts from pandas, setting the normalized argument to true. And now for each one in the categorical variables, we find the common list of labels, and we call common if they are present in more than 1% of the observations. We print them here, and this is because I need them for later on in the course. And then with numpy where, we're going to check if the value of that variable is in the frequent list. So if the value is frequent, then we keep the value. Otherwise, we replace the value by rare. We do the same in the train and the test set, but notice that the frequent list was determined over the train set. Here we can see the frequent list for all the variables that are categorical. And the final step is to transform these strings into numbers. We're going to create another function, and this one takes the train, the test, the target for the training set, the variable that we want to encode, and then the target as in the label. We create a temporal data frame concatenating the train set and the target. And now we're going to group by the variable, and we're going to determine the mean of the sale price in each one of these variables, and then we're going to sort them, starting for the one with the highest price to that with the smallest price. And now we're going to assign numbers to these strings that are ordered here, so that the label with the smallest house price will take the number 0, and the following label the number 2, and so on until the number of distinct labels. This is what this line of code is doing here. Here we can print the variable and the mappings. This is creating a dictionary, so now with this dictionary we remap the variables in the original dataset. Here we can see the mappings, so for the variable ms zoning, rare is going to be replaced by 0, rm is going to be replaced by 1, rh by 2, and so on. You can go ahead and explore these values. We're going to need them in coming videos. Some sanity checks. We can analyze that we don't have missing data. This is always useful because we tend to include them without wanting. And now what I want to show you is that this encoding creating a monotonic technique, which means that the higher the value of the encoding, the higher the mean sale price. So take a look at this code on your own time, but the important thing here is that the encoded m-zoning, the higher the value that we use to replace the label, the higher the sales price. So there is a monotonic relationship. In the street as well, in this at the variable as well, and feel free to explore the rest of the plots. So whenever there is an increasing difference, this encoding will capture it. To finish off, we're going to use the MinMaxScaler to scale the values of the variables between the minimum and the maximum. So we call the MinMaxScaler from scikit-learn. We fit the scaler to the train set. This will allow the scaler to learn the mean and maximum values for each variable. And then with the scaler.transform, we scale the variables, and because scikit-learn returns a numpy array, we're going to recapture this into a pandas data frame and then add the column names, both in the train set and in the test set. Here we can see the scaled variables. We're going to save the transformed data for the next notebook, and we're going to also save the MinMaxScaler utilizing joblib for a later stage. That is all for this video.